Okay, welcome to a lecture on Earth's geological cycle. This particular lecture is going to cover plate tectonics. The Earth's major geological processes are plate tectonics, and the next lecture will be on rock cycle, and then the one following will be soil formation. But all three of those are topics that are covered in something called geology, and geology is basically the study of the processes that occur on the Earth's surface and in the Earth's interior. So we'll be talking about both the surface and the interior in today's lecture, as a matter of fact. The Earth structure, this is a nice little cross section of what the Earth structure looks like. But basically what happened was that the Earth, when it was formed, after it cooled, it separated into these zones. And you have the core, your nickel, which is made of primarily nickel and iron. And the inner core is solid, the outer core is liquid. You have the mantle, and inner mantle is, they say, magma in motion. So therefore it is more of a liquid. But your asthenosphere, this is the kind of cool one. It kind of reminds me of caramel, or I actually can think of this better as silly putty because it is a fluid-like rock. So it's still viscous, it's still solid, but it moves. And what's interesting is that this is going to move because basically the core is so hot because it's going through so much radioactive decay in the materials that are in the core. And then you have the crust, and the crust has two types. You have continental and you have oceanic crust. And now continental is going to be composed more of your silica, and your oceanic crust is going to have more basaltic type of rock. So it is going to be more dense. So in other words, you're going to be able to, it's going to be more jam-packed type, more molecules per area. It's going to be just, I guess, the best way for me to explain that. And then I want you to notice the lithosphere. The lithosphere is all of the portion that would be considered solid rock. And what's interesting, if you look up here, the blue you can kind of see would be considered more of a, from here over, the blue over, all of this is your crust. If you want to think of the crust, think of it as the peel of an apple. So it's the thinnest layer of the entire apple, or the entire Earth would be your crust. But what I'm trying to show you with my drawing up here is that the lithosphere is not just the crust. It also includes this top part of the mantle right through that second grayish area. So all that right there is the lithosphere. From the asthenosphere up, all this is part of your lithosphere. And notice again, your continental crust is going to indeed be thicker. It's going to be thicker this way, but it's not as dense as your oceanic crust. See, oceanic crust is over here. I just learned how to use this drawing tool. It's pretty exciting. So, why do the tectonic plates move? You see, the earth beneath your feet move about the same that your fingernails grow. The velocity that your fingernails are growing is how much your plates are moving. But anyway, so what is creating these plates, in other words, the earth below you, to actually move? Well, they call it something called a convection cell or currents, where liquid rock is heated near the core and rises because it is hotter at the core, like I was telling you earlier, because of the radioactive decay of the materials that are found there and the heat and the pressure from all the other things being on top of it. So just like your properties of matter, something is heated, the molecules are going to expand and it's going to become less dense and therefore rise. But as you rise, you end up getting cooler and you will recondense and go back down. So it's cyclical. So you saw convection in your wind cells. Well, now you're going to see convection currents inside of the earth as well. Can anyone guess what area is going to be moving? Is it your inner core? Is it your outer core? Is it the asthenosphere? I'll tell you in a minute. Okay, types of boundaries. The three types of boundaries between the plates are divergent plates. And what happens at divergent plates, I'll show you on the next page, an awesome picture. Here it is. What happens at divergent plates, this is right here. This is divergent. In other words, pulling apart. So these two plates here are pulling apart from each other. This is one plate and this is another plate. It's pulling apart. And at that feature, you're going to have this hot magma rise up right along this crack. And it's going to form something called a ridge. And some of the deepest differences, like the highest mountains to the lowest pit, are going to be in the middle of the ocean here, because this is going to form almost like a mountain range. It's going to have this hot magma cool along the boundary. So that tells you, as the plate's pulling apart, the oldest rock is going to be out here. The newest rock is always going to be closer to this boundary here. So at a convergent plate, that's where you have your plates moving together. And there's several different things that can happen with convergent plates, depending on the densities of your plates. Remember how I told you the oceanic crust is more dense than the continental crust. Even though the continental crust is thicker, it is less dense. So let's look and see what happens there. So at a convergent plate where you have two different densities, whatever is most dense is going to subduct underneath. So here we go. Here we have the oceanic crust, and basically it is going to go underneath when these two are colliding. And you know, these arrows down here kind of give you an idea of which way the convection belt is going. So here you have this one's going this way, and this one's coming this way. So they are coming together. This plate and this plate are pushing together. And so the way I always like to think of this is that this rock is subducting down, and it's going to melt, right? It's hot down here. And as it melts, there's no two things can occupy the same space. And so I always think of this as, well, it has nowhere else to go, so it's going to rise up here, and then you'll have a volcanic chain right here, because wherever you have a subduction zone, you have all this magma welling up and has nowhere to go because this rock melts essentially and it just spews up here. That's just kind of how I like to visualize it. And a major feature on the ocean side, it kind of buckles right here, and it forms a trench. So those are features at a subduction zone. And by the way, remember, subduction only occurs when you have two different densities. Anyone want to guess what happens when you have a collision of two things that are the same density? I like to think of a sumo wrestler. When you see the two sumo wrestlers coming together, they end up kind of like they push together and then they rise up. Yeah, I think of that as more of a mountain. Okay, and then the last one is a transform fault. That's basically where you have two horizontal faults. Basically, it's just sliding past each other. And they could be sliding in the opposite direction, or sometimes they're sliding in the same direction, but one is just moving faster. But regardless, and that's what's happening down here with San Andreas, you're going to have the Pacific plates moving northwest faster than the North American plate is. And so it's going to create a lot of friction in those areas. Anytime you have plate boundaries sliding past each other, there's going to be a buildup of potential energy. So I'm alluding to something that's going to happen. We're going to find out about later. Okay, so this is awesome. You've already kind of looked at this picture a little bit here. Here's another good visual of it. You have your hot outer core here, and this is what's driving these convection belts, because this material is getting hotter. Gets hot down here, so it rises, and then it cools and it falls. So it's going to have the convection cell. Remember, hot things will expand, cold things become more dense, and they sink. So over here, again, this magma, always think of it as has nowhere to go, so it's going to form a volcano. Know that these divergent plate boundaries, when they're pulling apart, look up here. Also, this phenomena is called seafloor spreading. You'll see that, and the most famous one is at the Mid-Atlantic Ridge. And when y'all come back to class, I could show you my globe again, the big old one, and you can see it, you can touch it, feel the topography in the Mid-Atlantic Ridge. It's huge. But let's see. We have collisions between over here, two continents. If you have two continental, where's my cursor? There it is. You have continent, then you are going to have a mountain formation. And you can usually tell if it's a very active fault zone and you have two crashing, then you're going to have usually sharper mountains, in other words, younger rock. And some of the mountains are growing. When I say that, it's because the plates are pushing together still, so the mountains are still forming. So your internal processes are going to build up, and external processes, in other words, out from the inside of the earth, are going to wear them down. And I'll talk more about that again in a minute. Okay, this slide shows us the Earth's major tectonic plates, and if I were you, I would learn at least one specific example of each of the four types of boundaries I was telling you about. Okay, so the first one I'm going to show you. Okay, let's do, since we live on North America, let's talk about this a little bit. And on this graph, I'm not sure if you can tell, but the divergent boundaries are the ones that are going to be with the red line. Convergent show you, this looks like a little shark's tooth part right there. And transform faults, it's hard to kind of see on here, to be honest, because they're just black or like gray lines. But anyway, you know the Juan de Fuca plate. You're probably familiar with Mount St. Helens, Mount Shasta, Mount Rainier, and all those fun, the volcanic chain up in the Pacific Northwest. Well, the reason for that is because the Juan de Fuca plate is subducting underneath the North American plate. It's going that way. It's going underneath. Therefore, you're going to have a trench right here, and you're going to have a volcanic chain inland. So that's the common features you'll see at a subduction zone. You'll see a trench on the ocean side, and inland you'll find a volcanic chain. Okay, transform. You probably hear about California all the time. Oh my goodness, California's going to fall into the sea. Well, that's not possible. It is a piece of land. So continental crust is continental crust. It doesn't just fall over into oceanic crust. But anyway, what is happening though is the Pacific plate is moving northwest faster than the North American plate is. So it is sliding past the North American plate right here. And so that's why there's that's a major fault zone over there. Okay, so it's another specific example. Let's talk about a specific example of a continent-continent collision. Over here, you have India plate is smashing into the Eurasian plate. Why is that significant? Well, you have the Himalaya mountains over here, and these are some of those ones I was telling you about that just are still growing because that plate boundary is very active. Let's see, and then the last one, so that makes three. So the fourth one, let's do a division, right, where we have the divergent plate boundary. So up here, this one's going this way, and this one's going this way. So all along here, you have a divergent plate boundary, and right here is the Mid-Atlantic Ridge. And what's unique about it is that this is pretty common for your oceanic crust, but up here, you have a divergent plate boundary up on Iceland, which is cool, because remember what I told you what happens at divergent plate boundaries, that magma wells up in this area, and the newer rock is right here along the ridge itself. Well, that means Iceland has a lot of geothermal activity, which means they are able to tap into that, and they're using geothermal as a mechanism for alternative energy, and that's super cool. We'll talk about that more later too. Here's an example of the San Andreas Fault as it crosses part of the Carrizo Plain in California, United States. Very active fault zone. So we'll talk more about what happens at these fault zones. Oh, let's see if we can get this to play. Try again. All right, so according to the plate tectonics theory, the plate of Earth's thin crust are constantly moving apart at ridges and colliding at trenches. Click on the ridge and trench for more information about what is happening in that area. What do y'all think is going to happen when I click on the trench?
As a result of seafloor spreading, plates move away from the oceanic ridges. At times, two plates collide and the plates forced forming a trench at the boundary. Pressures at colliding plate margins cause earthquakes, volcanic eruptions.
Okay, now let's see what happens at the ridge over here. Whoa, okay, got that. So remember, your newer rock's going to be right here at the boundary. And you're going to have this right here is the trench. Up here, what's forming? What do you see? Look, this is melting. It's turning into magma. So this is going to come up here and form. This is going to be your volcanic island. Here comes the magma. There it is. This is your volcano chain. Oh, goodness, where'd you go? There you are. Okay. Here's another one. This will show you some more. I kind of alluded to what else do you think is going to happen at these plate boundaries. So now I'm going to give that. Okay, so we know, I showed you earlier where all the plates are. Remember, divergent are going to be red, and convergent are going to be your little weird looking things. And here are your transforms, are going to be the areas back and forth. I say weird looking things, I guess convergence, sharp.
The sites of
Okay, yeah. So if you notice on the slide that shows us right here, look, notice that there's a lot here. Okay. Anyways, I didn't mean to play that twice. I was trying to show you here, this is called the Ring of Fire, the Pacific Ring of Fire. In other words, there are quite a few disruptions in the Ring of Fire. There it is. Okay, so like I was saying earlier on one of the previous slides, the geological cycle, some parts of the surface build up and some wear down. Internal are going to build up. In other words, this is where your new rock is going to come from. Comes from cooling magma, or the fact that you have two plates crashing against each other end up changing the topography of the Earth. External, however, is going to wear down the Earth's surface, and this is because of sun and gravity. Weathering is physical, chemical, and biological, and I'll give you some examples of those later. And erosion happens. Okay, whoa, real quick before I get further. You have to know the difference between weathering and erosion. Weathering is the breakdown, okay? It's breaking down rock. Erosion is transporting, the transportation of rock, okay? And that happens because of wind, blowing water, human activities, and glaciers. Glaciers, when they retreat, they basically expand and retreat. And when they retreat, they can pull rock back. When they expand, they leave rock behind after they melt.